Assalamualaikum and hi students. So today we are going to learn about rate law and integrated rate law. So what is the rate law or rate equation? It is an equation that relates the rate of a reaction to the concentration of the reactants raised to some power. Alright, for example, I have this general equation. A mole of A reacts with B mole of B produces C mole of C and D mole of D. Alright, so how the general rate equation or general rate law looks like. Alright, so the general rate law is rate equals to K times the concentration of reactant A power of, let's say, X times concentration of reactant B power of, let's say, Y. Alright, okay, so A is the concentration of reactant A, B is the concentration of reactant B, K is the rate constant, X and Y is the order of the reactions. So X is the order of reactions with respect to reactant A, Y is the order of reaction with respect to reactant B, and if X plus Y, it is called overall order of reaction. Right? So rate law just relates the concentration of reactants and it is raised to some powers. Alright. So what is order of reaction? So if you look at to the general equation, you can see here X and Y is called the order of a reaction. Alright. So what is order of a reaction actually? It is the power to which the concentration of reactant is raised in the rate law equation. And it could be exponent of X, 0, 1, 2, 3, half, 3 over 4 and etc. for X. And it could be 0, 1, 2, 3, half, 3 over 4 and etc. for Y. Alright? Okay. And the order of a reaction indicates how much the rate of reaction changes if the concentration of the reactant is changed. Right? So it can determine how much of the rate of reaction will increase if the concentration of the reactant is changed. We will look at this example later on. And the order of a reaction is not related to the stoichiometric coefficient in the balanced chemical equation. It must be determined experimentally. Alright. For example, alright, let's say I have a reaction of 1 mole of A reacts with 3 mole of B produces 2 mole of C, for example. So, let's say given to you the rate law equation. Rate law is written as rate equals to rate constant K times the concentration of a reactant power of, let's say here is power of 2 times concentration of B. Let's say the rate law is rate equals to K times concentration of A power of 2 times concentration of B. But I can say that from the rate law equation, A is second order. Why? Because we can see here the exponent. It is power of 2. B is, actually this is power of 1, is first order. And overall order of the reaction is 2 plus 1, so it is third order. So you can see here the order of the reaction is not related to the stoichiometric coefficient in the balanced equation. It must be determined experimentally. Alright, the order of a reaction must be determined experimentally. Okay, rate constant. So what is rate constant? It is relates the rate of a reaction to reactant concentration. Alright, and it is a proportionality constant for a given reaction and temperature. It does not change as reaction proceeds, and it will remain constant if the temperature remains constant. The larger the value of K for a particular order, the faster the reaction proceeds. Alright, half-life. Half-life, the symbol is T half. Half-life. It is the time required for the concentration of a reactant to decrease to half of its initial concentration. Alright, okay, we will discuss it later. We will go one by one for each order. Alright, okay, so now let's start with zero order. So for your syllabus, we will learn zero order, first order and second order specifically. So now let's start with zero order. So let's say, consider a reaction. Let's say I have a reaction A converted to B. Alright. So if we relate to the rate law, okay, if we relate to the rate law, let's say this reaction is a zero order reaction. So the rate law is rate equals to K, the rate constant, times concentration of A power of 0. Because just now I said that, let's say this reaction is a zero order. Therefore, it could be written as rate equals to K. So this is the rate law for zero order. Okay, if you refer to the rate law equation, you can see that the reaction rate is not influenced by the concentration of A. The reaction rate, the rate of reaction is not influenced to the concentration of the reactant. So in this case, the reactant is A. The rate of the reaction is not influenced by reaction A. Let's say, what happened if I increase the concentration of A 2 times? Okay, rate equals to K times concentration of A. When the concentration of A is double, but since A is zero order, therefore the rate still remain constant. Alright, so if I sketch a graph, alright, I sketch a graph, rate against concentration of A for zero order. Rate against concentration of the reactant A. How the rate constant will remain constant, and it doesn't matter how much you increase the concentration of reactant A. Alright, you can say that the rate of reaction is independent of the concentration of A. And you must know that the unit of K, okay, the unit of rate constant for zero order is molar per second. Okay, so we will continue with the integrated rate law for zero order. Alright, so what is the difference between rate law and integrated rate law? Rate law, for example, this one, it relates the concentration, it relates the rate of reaction with the concentration of reactants and the rate constant at specific temperature. But integrated rate law, it is the relationship between the concentration of reactants and time. So it is different compared to rate law. Alright, so for zero order, okay, we use the same reaction A converted to B. Okay, for zero order, so this is the integrated rate law for zero order, where A is the initial concentration of A, AT is the concentration of A at T time, K is the rate constant, and T is the time. So you can see it relates the concentration of reactants and time. Alright? Or we can write the integrated rate law for zero order as, or we can write the integrated rate law for zero order like this. Alright? Okay. Okay, if we relate the integrated rate law with the linear graph, alright? Okay, we can plot concentration of A against time. So if we refer to the this equation, if we refer to this equation, concentration of A at T time equals to initial concentration of A minus KT, and if we compare with Y equals to mx, and this one is C, you will get a linear graph with negative slope. Okay, so from the graph you can determine the gradient or slope, which is equals to negative K. But the value of K, rate constant, cannot be negative. From the graph you will get a negative gradient, negative value gradient. Alright, okay. And from the graph, actually this is the initial concentration of A. Alright. If we use this equation to plot a graph, so you will sketch or plot a graph, initial concentration of A minus concentration of A at T time against time. And if you compare with linear equation, alright, if you compare with linear equation, so this become mx, this is become y equals to mx. Alright, plus c. So the c is not important here because you are going to determine the rate constant from the graph. So from the graph, gradient or slope, in bahasa Melayu kecerunan is K. So you will get a linear graph with positive gradient or positive slope. Alright, so how about half-life for zero order? Alright, at half-life, the concentration of A or concentration of reactant A would be half of its initial value. So from the integrated rate law, so this is the initial concentration, alright, and if we are going to determine the half-life, the concentration of A at half-life or T time becomes half from its initial concentration. So it would equals to K times half-life plus Thus, the half-life for zero order is initial concentration of A over 2K. So this is for zero order. Alright, so now let's continue with first order reaction. So let's say this reaction is first order reaction. So if we want to write the rate law equation, we have to refer to the concentration of A. Alright, so let's say this is a first order. So the rate law is rate equals to K times concentration of A. So it shows that A is first order. Alright, okay. Therefore, if we sketch a graph rate against concentration of A, if we sketch the graph rate against concentration of A, so you can see here, when the concentration of A increase, the rate will increase. So it is directly proportional. Alright. Okay. What happens to the rate of reaction if the concentration of A is double? So you can see here, when the concentration of A increase, the rate will increase. But how many times the rate will increase? So this is affected by the order of the reaction. Okay, so now you will please refer here. You can refer to this example. So rate equals to K times concentration of A if A is first order. But when the concentration of A is double, rate equals to K. Concentration of A is double. So what happened to the rate? You can see here, rate equals to 2 times K concentration of A. So what we can say? What is the conclusion here? So the conclusion is the rate of reaction is double, or the rate of reaction increases to time. So let's say here, the concentration of A from 0 molar becomes 2 molar. So what happened? You can see the rate increase. The rate is double. If the concentration of A is triple, increases 3 times, or the rate, if the concentration of A increase 3 times, so the rate increases 3 times, and so on. Alright? Okay. And the unit of K for zero order. So if you cannot remember the unit of rate constant, you can derive it. Right? How? By using rate law equation. Rate equals to K times concentration of A. We know that the unit of rate is molar per second. So let's say we want to determine the unit of K. So the concentration of A is molar. So molar and molar is cancelled out. Therefore, the unit of K is per second. Okay, let's continue. The integrated rate law for first order is ln concentration of T time minus ln initial concentration of A equals to negative KT, or we can simplify it and become ln concentration of A at T time equals to ln initial concentration of A minus KT. Alright? Alright, the graph from the integrated rate law. So, basically, for graph, for first order, alright? Okay, for first order reaction, there are few graphs here. So, first, graph for concentration of A against time. So, for first order reaction, the graph concentration of A against time is like this. Okay? This is a graph for first order, rate against concentration of A. For the graph that relates integrated rate law, we can relate it with the linear equation y equals to c minus mx. So we can plot graph ln concentration of A against time. So you can see the graph become like this, linear graph with negative gradient. So here C is ln initial concentration of A, and from the gradient, and from the graph we can determine the gradient where gradient or slope of the graph is equal to negative k. So if the question asks you to determine the value of k from the graph, the k value must be positive value. So the sign negative here shows the gradient is a negative slope. So this is the formula for half-life for first order reaction. So where half-life is equal to ln 2 over k, and you can see here the half-life does not depend on the concentration of A, the initial concentration of A. Alright, so settle with first order reaction. Alright, for second order reaction, so let's say this is a second order reaction. So the rate law is rate equals to K times concentration of A power of 2. So A is second order. What happens if the concentration of A is double? If the concentration of A is double, what happens to the rate? So rate becomes, what happens if the concentration of A is double? So rate becomes rate equals to K equals to K, concentration of A is double, to A power of 2. So rate equals to 2 power of 2 is 4. K times concentration of A. So if the concentration of A is double, you can see here the rate increases 4 times. So we can say that rate is quadruple, or rate increase 4 times. If the concentration of A is increased 3 times, so rate become rate equals to K times concentration of A, 3A power of 2. So rate become 9K times concentration of A. So you can see here, the rate increase 9 times, or by the factor of 9. Okay, so how the graph of rate against concentration of A looks like? So how the graph rate against concentration of A looks like for second order? It is like this. Okay, so this is for rate equals to K times concentration of A power of 2. This is what we have discussed just now. So rate, let's say the concentration of A is double. So the rate is quadruple. If the concentration of A increase 3 times, the rate increase 9 times. If we increase the concentration of A 4 times, the rate increase 16 times. Right? I hope you will understand after this. Right? Okay, so settle with rate law for second order. So now let's learn about integrated rate law for second order. So this is the formula for integrated rate law of second order. Alright? Okay. So now let's relate with the graph. Alright? Alright, so just now we have discussed the graph for second order. If the graph is rate against concentration of A, you will get this graph. Okay? If the graph is rate against concentration of A power of 2, alright, it becomes like this. Because it is directly proportional to the concentration of A power of 2. This one is concentration of A. Alright? Okay. If the integrated rate law is rearranged become like this, so we can sketch a graph. If we relate to the linear equation y equals to mx plus c, alright, so here is 1 over A against time. So you will get this graph, and this side is 1 over initial concentration of A. If we use this equation to sketch a graph, so we can sketch graph. So this is y, this is to mx, and the c is 0, right? So we can sketch 1 over initial concentration minus 1 over, we can sketch 1 over A minus 1 over initial concentration of A against time. So the graph is like this, directly proportional, and start from the origin. This one we have C, which is 1 over initial concentration. So half-life for second order is half-life equals to 1 over K times initial concentration of A. So the half-life is inversely proportional to initial concentration of A, and as the reaction proceeds, the half-life will increase for second order. Alright class, so this is the basic knowledge for rate law and integrated rate law, and you will apply this when you are going to solve calculation problems for each reaction which is related to rate law and integrated rate law. So I hope this video helps you a lot. Alright class, thank you.